Hello, thank you for attending to this new webinar. Today we will, Roman Martin and Ronald Siat will talk about how to model nonlinear concrete using CivilFEM PowerMark 2019.
Well, hello. We are going to see how to model nonlinear concrete and using the different input data that is needed for a realistic accuracy simulation. First, we will have an explanation of the software we are using. We are using CivilFEM 2019 powered by Mark. That is a software from MSC Software. And then we will follow different examples, different concrete beam tests, and also we compare with real tests, real concrete beams. We will modify in the same beam, we will modify the reinforcement. So depending on the reinforcement we place, we will have different type of failures in the under reinforcement beam. For bending, we will have a failure due to bending, just tension steel. Then we will have an over-reinforced beam, then the failure will be due to compression, and then we will have also shear failure, just not adding the stirrups, the shear reinforcement. We will improve that shear failure model with fiber reinforced concrete for the same beam, and also we will see the difference between embedded and bond slip reinforcement. We can insert reinforcement into concrete, so they will work completely together, or we can add bond slip behavior. Just when there's a higher stress for corrugated reinforcement, that highest tension stress will break concrete between corrugated bars, and then slippage will happen. Also, we can analyze that. And then we will have a fast overview of other options, other nonlinearities such as creep, also syncrates, and construction states with activation and deactivation of the elements. And not only that, but also time-dependent material properties that are updated following the concrete age. And finally, also the options for thermal structural couple analysis. So, well, first we'll have an overview of the software that is CivilFEM 2019 powered by Mark.
Yes, just to let you know that you will have a multidisciplinary software which will cover all the civil and structural engineering fields, geotechnical, construction, and as you can see, all these types of models for construction, the seismic, foundations, power plants, all type of major infrastructure from the initial analysis to the end.
It's a general purpose civil structural and geotechnical software that is focused in construction and civil engineering, and well, we are using a nonlinear solver, so it combines high nonlinear models with also code and standard verifications and some other tools. And what the solver is Mark.
Yes, as you know, there's a big and reliable trusted group behind this software, MSC Software, which the developers and distributors famous Patron software, and because an agreement with MSC Software and between them and NG we build and market CivilFEM powered by Mark.
Well, it says we are using the most advanced nonlinear solver from MSC Software. MSC Software are the company that develop Patron, Astran, and so on. So we are using a high nonlinear solver, but with combining with CivilFEM, focus in structural, civil, and geotechnical engineering. And well, just let's go with the examples we are going to do with this software. It's very suitable for this type of nonlinear analysis focused in civil engineering. Well, first for concrete modeling, there are different data that must be set. First, for the cracking and crashing behavior. So, well, first for cracking, we have to input a cracking stress, and after that cracking stress, we can have a brittle behavior that is suddenly lost of the stiffness. We can add a softening modulus, and also we can add through a table hardening and softening for modeling fiber reinforced concrete. Also for compression, we have this type of parabolic loads with that could follow nonlinear compression isotropic hardening with unloading and loading curves, or Boudica-Sutz plasticity. And also tracker bracket series failure can be added to the model. And well, cracking and crashing is analyzed in principal stresses. Well, just the first example is under reinforced and under reinforced beam. But before checking the first example, I'm going to have an overview of a small overview of the software. Well, first, the software CivilFEM, just starting a new analysis, you have different options to generate the geometry, points, lines, volumes, Boolean operations as any other CAD. So it's easy to use. Also, you can copy, paste the different copies. So it's very fast and easy. Also, you can import from any CAD, so you can import it. This model, just for not to waste time, I've already generated the models, but just this is a volume. This volume will be meshed with solid elements for concrete. Also here there are some lines. We will use these lines for boundary conditions on bottom and to apply loads. So we will apply 2 vertical loads. It will be a simply supported beam. Well, we will generate the model with solid elements for concrete, link or truss elements for reinforcement, and we will change different reinforcement configurations for analyzing different possible failures for compression, for cracking and tension of the reinforcement, shear, or different type of failures. So well, the first, once we have the geometry, then for the modeling, this is a office-style software, so we have to go from left to right, following the different tabs. After generating the geometry or imported it, just model, first selecting elements. If we have for beams or trusses, just the cross-sections, concrete, steel, generic, and then we mesh. For concrete, we select a concrete. In this case, it will be HCI called concrete, and we click here, this one. We will use it. Just clicking, we are selecting this material from the library. So all properties, all code properties are automatically defined here. For example, elasticity modulus, and them all are time-dependent properties. So in the model, we can solve for different agencies, and CivilFEM automatically update all these properties. Well, for this type of model, I would like to solve with a nonlinear behavior. So well, first, clicking here analysis, I will use for tension analysis, I will solve short-term loads diagrams. So clicking here, this diagrams is in the analysis diagram, short-term loads, this is the table that is going to be used. As I said, it is time-dependent properties, so I have several days with several stress-strain diagrams. When solving for different agencies, CivilFEM will take one of these and will just change one for other if I'm solving the model for day 5, 10, 15 for evolutive stage analysis. Also, well, it could be done with Boudica-Sutz plasticity model or isotropic plasticity model. I'm going to use isotropic plasticity models with loaded and unloaded curves, follow the elasticity modulus and plasticity deformation, which will be easy to plot those plasticity deformation. Well, that is for concrete, nonlinear, for compression, nonlinear behavior. Let's see for tension. For tension, the first option is setting cracking. If I set here cracking, I will have crack stress. Just if I see the slides, here this will be the crack stress I'm setting. It means this is the crack stress I set. When I will have elastic behavior for tension, when I get this crack stress, I could have a suddenly failure of the element. I will have a vertical load. Then I will have deformation without stresses. Or I can have a softening load or hardening and softening, depends if I'm modeling fiber reinforced concrete. So the way to do that is here in the model, just softening modulus 0, it will be vertical. I can add here a value. In this case, it's a softening value, depends on also the properties of concrete, or it could be variable. It's variable just with here in this table, an example.
Yeah, you can always customize this table to your needs. And later you will see the different charts that we have for all the options because we will show you many models using constant or variable.
We could have this variable softening modulus that it is in this case it's a straight line, but we can have different points. An example I would add here.
The shear retention factor can be variable as well.
So I can have different softening loads, hardening, any type of table can be set. Also copy and paste from Excel table. So this will be the behavior for softening after cracking behavior to model. Also, a very important value is variable shear retention. Shear retention is this value is the coefficient that multiply the shear stiffness. So it means in a crack, once the element has gone over the crack stress, we'll have crack strain. In those elements after cracking, the shear stiffness will be multiplied by this value. So in this case, I've said 0.5. It will mean it will have half of the original shear stiffness before cracking. Well, it's a high value, and this could be good for models with small cracks and with a lot of reinforcement crossing the crack, because this is about the friction in the crack between both sides, and also possible stones and other material crossing the cracks that join it and allows a percent of the shear crossing the crack. But the most accurate is just defined through a table. In example, if I set this, I will have when crack width is 0, I will have 100% of stiffness. When crack is 0.001, no shear stiffness. This means that when in the model we will have a crack crossing the model, it will become a mechanism when the crack width is 0.001 and it stops converging and it collapses. So these curves, you have many information in the internet. This used to have a parabolic shape, something like this. So it could be something more similar to so it should be something more similar to this. Okay. Well, once I define all these properties, I generate the mesh, just also the materials for reinforcing steel that I'm going to use ICI code, and it's just I'm going to use this one in example, and I click here the analysis, and also I'm going to use a bilinear stress strain diagram. Could be okay, and also here also just for the model any cross section. This is a circular section. I can add here millimeters, for example, 60 millimeters diameter for my bars, and well, just create the mesh. So well, for the mesh, first for the solid elements, I'm going to create just for the beam the concrete material. Click here, and then I create mesh controls. I'm going to extrude the surface to have control in the section and in the extruding direction. As I need a very accuracy model for crack developments and so on, I'm going to create a mesh like just an example, this one with 2 centimeters in the section, this element size, and 1 centimeter or 2 centimeters, in example, in the length. So well, just click in mesh. I generate the mesh of this. Here you can see the progress meshing. I generate the mesh for this.
Yeah, the finer the mesh, the more accurate you have, but always yes, you can perform a estimation.
In the same way, just I can generate the reinforcement. So well, I'm going to add this reinforcement for bottom reinforcement. An example, this one and this one, and just clicking here, I generate. Here you can see I've generated 2 trusses, that is reinforced 1 and reinforced 2. and just the name for 2, and just also I mesh both. Well, once I have meshed both, I just have to insert one into the other. You can see I don't have a congruent mesh, so I cannot merge the elements, the nodes, but I don't need. A very important tool in CivilFEM is the insertion. If I click here insertion, I'm going to insert in this element, this model, I'm going to insert the 2 other rebars, which is this one and the other one. So with this tool, sorry, this one, with this tool, I insert reinforcement into concrete, and them all will work together.
Yeah, you will couple the degrees of freedom of each entities.
So well, just I did all the examples following these options, but I modify the bending reinforcement diameter and the different reinforcement configuration, and apply a load, 2 loads on top at a distance of half meter from support. It have 1.5 meters span length, and just apply loads with different reinforcement configuration, analyze the possible failure.
Yeah, you will see them in the slides now.
Also very important, I just set for compression, I will have a parabolic load, will load it and unload it. But if I would like to have a brittle compression behavior that is crashing, I have to set here crashing and analyze the strength for crashing. Codes limit strain for concrete, compression concrete to 0.35 or 0.3%. So in this way, I will have also crashing failure. So well, we have completely defined all non-linearities. Just then going to the models, let's see different concrete configurations, and well, the next option is applying a load and solving it. So just the first model under reinforcement beam, what I have is here on bottom 2 bars of 16 millimeters, that is 200 square millimeters, not of reinforcement, just shear reinforcement to avoid shear failure, and apply 2 loads. Once I apply loads, I increase that loads till failure, and analyze the different failure that happens. Also, these examples are compared with real test. You can find this real test in Structure Pro, and here they have in videos. They have analyzed here in these videos. They have they have different tests where they apply loads till they break those beams and get the relationship between loads and vertical deflection. So we follow the same examples and compare real test results with CivilFEM results. You can find these videos in Structure at YouTube. So just analyzing first example, just if we go to the software, just under reinforcement, this is the model we had. Here, this is the load we added. So here you can see simply supported, 1.5 meters span, 20 centimeters at both sizes, loads on 2 points at half meter, just half meter from every support. So half meter to first load, half meter to the other, and half meter. And we apply load till collapse. Till the model collapse means not converting because the model breaks and not converting. So it has been solved in 25 steps. And well, if we plot in one of these points a vertical displacement versus the load, we get this type of curve. We can see this case we have like a ductile behavior. First step here we have like a modification, so it could be means cracking starts, but mainly elastic behavior. And then we have like here a horizontal branch, a maximum load that we can apply is between 35 and 40 kilonewtons, and this behavior. So well, let's see what's happening in the model for these points, for the last one. So just going to the last load step that will solve. I'm going to plot first. Okay, here in the model, I'm going to plot first cracking. So I'm going to plot here maximum principal cracking and plot it. Okay, I can see I have mainly bending cracks in the center. Just as I have here high with cracks, just to be able to see the rest, I'm going to reduce a little bit the range. So just one and plot here. Well, I can see I have mainly bending cracks and no, just not high shear cracks. So I can imagine this is mainly having bending failure. So if I hide the concrete part, yes, and plot the reinforcement bars. So let's see if yielding is happening. As I saw here, I have 2 bars of 16 millimeters. So I'm going to plot the equivalent plastic strain. Example. I can see I have high yielding values where the crack were generated, and only for bending, but no yielding for compression reinforcement and for these parts. Okay, so well, results quite good and just what was expected. I'm going to plot the crushing zone. As I said, I'm using isotropic plastic modeling, so compression deformation is analyzed by equivalent plastic strain. Here in my material, you saw that I have limit crushing to 0.0035%. So it means when it reaches 0.0035, there's a failure. So I can see in this model I have at the end a compression failure crushing in this zone. But I also have yielding and cracking, high cracks here. So well, I can see I start having cracking. Let's plot this point. So I can see I have first crackings. Low compression strain, very low, but crackings. And still yielding. And then the final step is just high cracks, still yielding, and final we have compression failure at the end as well. So well, let's see the slides.
You can see we can monitor each step of the analysis.
Here, this is the tests that were done, and you can see here you have at this horizontal branch, which is between 35 and 40, close to CivilFEM results. High cracks start mainly in the center and vertical, so they are not high shear cracks, so it's mainly bending. And then when we have this suddenly collapse, you can see here also a piece of concrete is broken due to compression. So we have first cracks, yielding and reinforcement, and this is under reinforced. It means it is yielding and getting high values. So well, if we compare values, we have crack patterns that are very similar, vertical, mainly in the center, vertical and not much shear, and also crushing zones in the center, similar to the ones we get. Here we have a video. In this video, you will see a point moving here, that it means the real test, load versus deflection. And here we will have the same model, but in CivilFEM. So here you can see that cracks starts, vertical cracks as here, then they are increased a lot, the horizontal branch, and then suddenly collapse due to compression, more or less in the same time. So if we compare both curves, we can see they start at between about 36, 37, similar to CivilFEM. CivilFEM, this curve is more horizontal. That is because yielding in steel, we have a horizontal branch. There is no hardening for steel. The real behavior of steel has a hardening, so this curve has a hardening that we didn't add. And due to that not hardening, we have a more suddenly behavior earlier due to compression in concrete. So well, the accuracy of CivilFEM, you can see, is very, very high.
Yes.
Next model, very similar, but in this case, we increased a lot the bending reinforcement. We have increased it up to 20 millimeters, the diameter from 6 16 to 20, and we have increased the area from 200 square millimeters to 600. So now, and also we don't have here compression reinforcement, so now just the behavior we expect to have failure due to compression and not much yielding on reinforcement. Okay, so just analyzing the next example. We can see here, let's plot results. We are going to plot the same result. Now the model stopped converging with 23 steps. And if we plot the curve, we can see we have more or less a linear behavior. And then at this point, suddenly, completely a loss of the stiffness of the beam, and the two steps are without any type of force, of reaction force from the beam. So what I'm going to plot, not the last, because the last only just 3 for that, 19, 20. So let's see what's happening in my model. First, I'm going to plot cracking, maximum principal crack strain. I can see I have some cracks developed here. I'm going to plot average values, but they are not so much as I had before. Bending cracking, but they are just small. I mean, they don't cross all the section as they were doing. Some cracks. Let's see what happens with reinforcement. In this case, we are having, let's plot equivalent plastic strain. And we can see there's no yielding, so well, we are not having problems about tension in this model, no yielding in steel. You can see between 0 and -0, green is no yielding. And now let's plot what's happening in concrete. Concrete equivalent plastic strain, which means compression failure. So well, we can see just on the points where we are applying these loads, we have higher compression loads, and in this load step is around 0.25%. We increase that value. We just advance, we increase the load. So just in this step, it's 0.29.
This is the undeformed shape, but we can always plot the yes, deformed shape as well.
So we can see that in step 21, this is the deformed shape that can be scaled. 3 an example that is scaled plot. And well, we can see at this point we have almost, and we are almost in the limit, 0.0032, and limit is in 35. So well, next step, it collapses and it doesn't convert. It was what it happened, the model breaks down. So well, those are the results as we saw here. Results comes here, and then compression of concrete, and suddenly collapse. So it's a brittle behavior of concrete when it is due to compression over reinforced sections. So if I see these results, I can see here the test compression is broken from the supports, from the loads that I am applying, 2 different loads at ½ meter. Here we can see we are applying a load here and another load here. So we have failure instead in the center, as we saw before. It starts where we are applying the loads, and also in the test, as suddenly collapse at 90 kilonewtons. So if we compare the crack patterns, not high cracks for bending, I mean not penetrating a lot, short, similar. CR are longer, but not very wide, and crashing zones, which is the most important, and which is the failure of this model. So here in this video, we are going to compare the real test. Here we will plot cracking, and here we will plot compression, deformation, and crashing. And this we will see just the load, the relationship between load and displacement and vertical displacement. So we can see first cracking has started appearing here and here, similar. CR crackings has started appearing, and then here just crashing. Crashing happens. Let's see the video. First, just again, cracking the bottom of the test and also in CivilFEM model. And well, sorry, I didn't play both. same time. So now we are playing both cracking in CivilFEM model and in the test. And just when we are reaching the maximum load, here we can see crashing at the same time that it happens in the real test.
Yeah, the accuracy is very high.
Yeah, and we can see deflection versus load. It happens at about, in the real test, about 14 millimeters and 90 kilonewton. And with CivilFEM, it happens with a lower deflection. So we are having just like 90 kilonewtons and 11 deflection. So the accuracy is very close. I have to say we are using code and standard values for this, just concrete as a small variation. So maybe testing the real compression behavior, the real relationship between compression, stress-strain relationship, we could have a much more accuracy results. Next model is CR failure. So the CR failure, in this case, we are not adding CR reinforcement. We are not adding strip wraps here. So only bottom reinforcement. This bottom reinforcement is the same that we had in the last over reinforced bending, but only just removing that. So just checking the model as we did before. The CR critical, here is the model. I'm going to plot vertical displacements versus load. Here we can see we have the same, more or less, a linear elastic behavior, and then suddenly failure due to these cracks. I'm going to plot the last point, see crackings, and what happens between this and the other. Well, I'm going to start plotting this one, and let's advance to see how cracks are developed. So I can go to
last one.
This one, an example, which is still in this linear behavior, more or less linear, and I'm going to plot crackings. I can plot cracks in X direction, Y direction, or maximum and minimum. Well, I can see here, these are my cracks. And well, I'm going to just fix the range for not having a very, to appreciate all the cracks. So well, I have at this point some cracks, but not very wide. Mainly here I can see some CR cracks are higher than the bending ones, both sides, but still not too high. So I increase the load, advance to next step. Next step. You can see cracks, CR cracks are developed from following 45 degrees from supports. Suddenly a huge crack is developed, so it means collapse at this point, which is this point here. And then we have some other steps that were solved, but well, you can see this is just completely collapse. So we could suppose this is the ultimate load for this model. I increase, you can see, well, now the crack is almost crossing all the model, and this is just converging because we still have some steel that is joining both parts, crossing from one point to each other, and then finally it doesn't converge. We could see also yielding bottom, but well, we can see that it's very clear that it's failure. So just if we compare with the real test we had, here you can see the model is the same, and here you can see that CR cracks are developed, high CR cracks, and also we have the same type of behavior, like vertical and suddenly collapse. Crack patterns are very similar between the real test and CivilFEM. And well, here we can see the real test with the load versus deflection, and just now pay attention to the CR cracks that are being developed. So just in videos, we can see we start with some bending cracks at the same time, then CR cracks are developed and collapse happens in the two videos. Then if we analyze the curve that is obtained with CivilFEM, we can see that at a deflection of between 6 and 8, around 7 and 40 kilonewtons, collapse happening. is happening just in the real test. It happens a little bit for the same load, for higher load about 45. Ours is a little bit under 45, and also more or less the same behavior, but also just brittle behavior, just crack, no ductility with this. Well, so for increasing ductility in this model, we are going to solve the same model, but we are going to add a fiber reinforced concrete. The way to add fiber reinforced concrete is just modifying the post-cracking behavior. So here, concrete cracking, and I can see this here, shear variable softening. What I'm doing is adding this load. After crack, this is post-cracking behavior. So after crack, I add a hardening, and then softening with high deformations and a remaining strength. Well, this is similar to the typical behavior that we can find with fiber reinforced concrete. After crack, we can have hardening and softenings if we have a high fiber reinforced concrete, or if we have low fiber content, it will be like a softening but with this small behavior, not as solidly. So I add high content. So well, just checking the model, we can see now it is exactly the same model that had the shear failure. I'm going to load all of this, and also, well, just in one of the bottom nodes.
I'm going to plot here again the reaction versus the deflection. We can set any kind of units. We will set displacement in millimeters and reaction force in kilonewtons, for example.
So if we plot this, we can see the previous model just collapse happened about between 40 and 45 kilonewtons, and with 6 millimeters. We can see now we have we increase the behavior, and also we have a ductile response of the structure. I have to say, I applied I stopped the calculation when it reached 1.2 centimeters, but it was converging. It means here I didn't have collapse. I just had just horizontal branch, a very ductile behavior. This is not the last point. I solved just till here. You can see in boundary conditions. I just solved till reaching 1.2, but it keep converging. So the ductility is much higher. So here, comparing both results with and without fibers, the behavior is much better. And well, here you can see the two videos. Here is without a fiber, and here is with. You can see cracks are much higher here, and we develop shear cracks. Here are much more split cracks, and mainly we are having these bending cracks, but not collapsing, and you can see it lasts much longer. It can support much longer loads. So now the last example. We have consumed most of the time for this webinar. The last behavior we would like to see is bone and slip behavior. So at the moment, you saw we have inserted reinforcement into concrete, so it works like completely embedded reinforcement, completely bound. But for this type of behavior, you can see that in corrugated reinforcement, we have first an adhesion, so they work completely together. Then some cracks start and some crashing zones start, and so we will have this behavior like cracking and failure of the concrete keys between corrugates. And then once they failure, the only thing that have between reinforcement and concrete is friction. So the way to add this into CivilFEM is adding cohesive contact between the rebars and the concrete. So I added this behavior and on with this table. So here you can see on the slip. Now this model is similar to the previous one, but what I did is just modeling here the reinforcement also with solid elements, and I added contact behavior between them. The way to add those contact behavior is very easy. Just select contact. Contacted part is the concrete. Click here. Contacted part is one reinforcement and the other. So I have contacted solid reinforcement. Click OK. And then I define this behavior. It can be glue reinforcement or just it will be completely embedded or cohesive constant. And this cohesive, I define normal direction. Normal direction will be completely contacted, automatic, and just shear, tangential direction. So if I click here, I will have bound slip behavior. And I define it that bound behavior by bound slip behavior through a table inserted stress versus strain. Well, as I had previously done this model, just this is my contact behavior, and this is the stress displacement curve that I have added. Well, solving the model, I have solved the model 2 times with cohesive and with glue contact. So here, just I don't have much time to show the videos, but you can see that the model with cohesive, they have similar behavior between the glue and cohesive, but at a certain point, slippage happening, so then there's a deflection, high deflection, without and reducing loads, and then once slippage happen, just with higher deflections, we keep having some stiffness that are increased, even if we don't have just a completely bound behavior between reinforcement, but it still have some, well, you can increase loads, but you can see there's a high difference between good anchor distances for the unoverlapping distances between reinforcement, that you can keep like this linear behavior, and the others that you have this loss of stiffness due to the unbounded just the slippage in concrete.
Yeah, you can simulate the pull-out very
yes.
accurate.
Yes, this is for, you can simulate pull-out of anchors, just any type of anchors, reinforcement inside concrete, so this type of tool is very useful. And well, just the last example we are going to see is creep. Also, we don't have much time to see this example in detail, but just for you to know where to set these values here. Creep for the creep model in concrete material, very easy as well. Concrete, we saw out cracking, crashing, and then for creep, we have to update here creep. Instead of no creep, solve step by step, and select the code we will have to add. Also, we have to set relative humidity, equivalent thickness, and well, creep coefficient depends on the update table. Just setting these values, also we could add sink rates. We apply a load and solve following a calendar time. The calendar time, very important here in materials, you have the activation time. It means this is the day when you place concrete. If I set it to 0, my concrete of this column is placed on day 0. Then for the load cases, when I'm solving the different load cases, in example, the first load case, I will solve it for the calendar time 10 days. CivilFEM will update material properties to 10 days and also will apply this load during 10 days to calculate creep. So well, we solve different load steps for different edges from 10, 25, 90, 365, and so on. And so we solve considering creep. So we will have different results, strain, stresses in concrete, and also in steel, because this is a reinforced concrete column with inserted reinforced. So we can consider creep. And very important, this calendar time is very useful also for construction process. In example, if we have different concretes, different activation time, in example, I concrete first this the day 5, so I should set here day 5, then if I add over that a slab, 10 days after, so my activation time I will set the days after. So using this calendar time, I can perform really accurate construction stage analysis, considering time, and CivilFEM will activate material properties stiffness, and anything, any material properties will be updated during the stage process. So just this stage process can be used for calculating creep. In example, here you have the different days, and first is the creep strain. You can see the creep strain is increased for the days. Also, stress in concrete. The stress in concrete, the stress in steel, sorry, is increased. Why? Because of the concrete creep. Concrete creep makes steel that is not having any creep increase the stress, and in concrete this stress is reduced because the form itself is the same in both. So in one get higher stresses. And also this calendar time can be used for any type of construction stage. In example, this bridge, different parts, every part of them has different concrete material, and in them, well, the activation time is different. So we solve different load steps with a calendar time. So what you can see, just CivilFEM material, concrete nonlinear material model, can consider cracking, crushing, also evolutive stage analysis, and the last point is thermal structural analysis, coupled thermal structural analysis. In this case, this example, we applied the effect of heat generation from cement hydration. So we set the law for this volume that generates heat. This heat is being reduced for the days. And well, also we added on top ambient temperatures, and also we consider around it the isolation due to the casing around it. So well, this is good to calculate in example the height of the new concrete blocks over all one to avoid cracks due to thermal stress. In this model, we have measured on top, middle, and bottom of the new concrete temperature. Top is the blue one, which is affected by ambient temperature day and night. The middle, which is the one that get higher temperature, that is this one, and bottom is the other, the green one. And we can get not only temperature but also stress temperatures. Top, we have these tension stresses, and we can see if we will develop crackings due to thermal stresses on top. And also, well, in middle and bottom, it is under compression, so we don't have tension, we have compression, so we'll have no problem of cracking. This is other example that we can solve. So we can mix thermal structural coupled analysis with evolutive stage analysis and cracking, crushing, and all type of failures. So well, as a summary, you can see concrete material model is very powerful, accuracy, and also the most important is that converts very fast and easy. So well, we can model cracking and post-cracking behavior, tension hardening and softening, very important shear retention factor, which is the factor that multiply the shear stiffness. For collapse, we have to set the table that this shear retention factor will depend on shear crack, on crack. So that's set to 0. Crushing with a strain for crushing, codes set it to about 0.3, 0.35%. Also creep and sink rates for strains, long-term strains. For reinforcement, not only passive reinforcement, also active reinforcement. I mean, we can model tendons, reinforced post-tension concrete. We can have yielding reinforcement, and also embedded or bone slippage behavior, and construction process activation, deactivation, and time-dependent material properties that are activated, mixed with thermal structural analysis, so very detailed analysis of concrete. And well, applications are many. It can be applied to any concrete model. CivilFEM also can design this structure under codes and standards. That is good for slabs, beams, and so on. But in distributed regions, such as this being called joint, this type of nonlinear analysis with cycling loads or any other transit analysis should be done, because, well, just code and standard cannot be applied to distributed regions. We don't have, we cannot apply Navier-Stokes hypothesis. And also, well, we can obtain capacity curve for crucial level analysis, failure analysis, well, or any type of advanced analysis. And well, It's very important to analyze models also under nonlinear analysis, not only linear analysis and code and standard verifications, because in this way you can, as we saw, you can address safety issues of the structure, just analyze if they are brittle or ductile. Also, we can see what's happening with higher design loads, conditions, and if it will collapse, suddenly collapse, or just they will keep just a small remaining stiffness and ductile behavior. And in this way, we can optimize our structures. So with CivilFEM, you can see it's very easy to perform this nonlinear analysis, just code, standard verification, any type of analysis. And well, just as you say, well, as you saw, just is very powerful for this type of
for
civil structural analysis.
Need more information, you have our website of our company, of our software, CivilFEM, and the way of spreading all our knowledge. We have our international masters and another e-learning platforms, and besides our social media, Facebook, YouTube, Twitter, and LinkedIn.
If you would like to learn more about finite element analysis, then don't hesitate to contact us. You can also have a trial version of the software, and we can answer
demos.
Yes, we can perform a demo for you, just if you are interested in the commercial version of the software, and also any further training. We have two different courses.
International Online Computer-Aided Engineering Education Center with many courses, just to practice with the software. But if you want to include the theoretical and fundamentals, you have the masters, UNED masters. Now registration is open for the 26th edition. And if you want information regarding sales, you have the commercial department. Christina Rodriguez will be very pleased to attend you. Visit our websites, and
we have a very realistic pursuit condition. Just as for many of you, CivilFEM is new. You could also rent or just check that the software is very suitable for your conditions, and finally get it. Also, you can get some more information about CivilFEM in our website. Just civilfem.com. Here also we have some videos, webinars, and also for you all. Sorry I couldn't answer all your questions you were doing.
You can use this tool to place your questions, or use the.
Yes, you can ask all the questions that you did. I will be answered in the following hours. Sorry, I didn't have much time to answer on just live, but also email us for further information, and I will answer all your questions you have.
And please, take just a couple of minutes to fill in a short survey after this webinar ends.
And any suggestion for further webinars and information, you will be very welcome. Thank you.
Thank you very much.